There's one more situation that I want to look at as far as static equilibrium goes, and that is a brick on a ramp. So remember, for static equilibrium, we have that the net force is 0 and there's no acceleration. So that means that our object is either not moving or it's moving at a constant velocity. So if I have a brick on a ramp, let's draw a free body diagram of that. So for my brick on the ramp, here's my brick. So the forces acting on my brick, I have the force due to gravity acting straight down. I have my normal force, and then I have a force of friction resisting that motion. Now looking at this, if it's just sitting there, I've got the ramp tilted but just a little bit, I'm going to have balanced forces. So let's look at what that means. Well, first of all, this force due to gravity, let's break it into the components. So, if this force due to gravity is mg, this one here, this force parallel to our ramp, is going to be mg sine of our angle, and this force perpendicular is going to be mg cosine of our angle. And recall that this angle is the same as the angle of the ramp due to similar triangles. So if we have balanced forces here, that means that all my forces perpendicular to the ramp must be balanced, and all my forces parallel to the ramp must be balanced. So perpendicular, I have then that Fn must equal my other force perpendicular, mg cosine of my angle, and then parallel to the ramp, the force of friction must equal mg sine of my angle. Now one thing to note here is that my force of friction would not necessarily be the maximum force of friction it could be. So as you tip the ramp up, then finally the brick is going to start to move, right? I can tilt it a little, nothing, tilt it a little more, nothing, and then all of a sudden it'll start to move. So let's talk about at the start of the motion. So I've tilted the ramp just for the brick to move. So at the start of this motion, that would mean that I have the maximum force of friction. The forces then, just before it moves, are almost balanced. Close enough, we're going to say they are. So when we're talking about friction, we have this funny thing called mu, and mu is just the ratio of the force of friction to the normal force. And we'll do a little bit more of a fact. But force of friction, I said, was the same as mg sine of my angle. And my normal force, I said, was the same as mg cosine of my angle. Whoa, I've got mg over mg, that'll cancel. And I'm left with sine over cosine, which hopefully you remember from trig is tangent of my angle. So I have mu is equal to tangent of my angle. Won't use this a lot now, but it will come in handy later.